Now this is going to be a lesson on the Pythagorean identities. Now as the name implies, the Pythagorean identities have something to do with Pythagoras' formula. To show you exactly what they are, we're going to need to start with a unit circle. Now I quickly want to review what it means for a point to lie on the unit circle. Let's start by picking a point that does not lie on the unit circle. Now the points that are on the unit circle can be thought of as the set of points that are exactly 1 unit away from the center. Now we're saying that this particular point that I've chosen is not on the unit circle because its distance from the origin is not exactly equal to 1. Now to actually find the distance between this point and the origin, we can just go ahead and draw a triangle beneath it. Now to find the length d, we can just go ahead and use the Pythagorean theorem. Now 0.4 is the same thing as 4 on 10, and 0.6 is the same thing as 6 on 10. Now we can just expand squares to both the top and the bottom, and then we can write the fact that 4 squared is 16, 6 squared is 36, and 10 squared is 100. Now 16 plus 36 is just the same thing as 52. Now we can take the square root of both sides, and we notice that d is just root 52 on 100. Using our calculator, we notice that d is just 0.72, and therefore it's actually not equal to 1. Because the distance isn't exactly 1, then this point does not lie on the unit circle. On the other hand, let me go ahead and draw a point that clearly does lie on the unit circle for you. So this point at 0.8, 0.6 is actually on the unit circle. And to show you that, all we really need to do is to do Pythagoras again. Now this time I'm going to be a little bit lazy. I'll just go ahead and take the square root of both sides straight away. And then I'll type this whole expression directly into the calculator. So when we do this, we notice that d equals exactly 1. And this basically confirms our suspicion that this point is in fact on the unit circle. So now we can get rid of this working out and move this point to a random place on the unit circle. Now if we let the radius of this circle be r, then for any point on the unit circle with coordinates x, y, we know that x squared plus y squared just has to equal r squared. But since the radius of any unit circle is just 1, then we can say that r is equal to 1 as well. Now suppose for a moment that this point made an angle of theta to the x-axis. Then as we already know, x is the same thing as the cosine of theta, and y is just the same thing as the sine of theta, so we can go ahead and mark that on the diagram as well. Now something pretty interesting is going to happen if we perform Pythagoras on this triangle again. But instead of using x and y, we're going to go ahead and use cosine and sine. So when we perform Pythagoras, we notice that the cosine squared theta plus the sine of squared theta is equal to 1 squared. Now this is actually a pretty interesting result, and I'd like to actually test it to show you that it works for pretty much any point you'd like. Suppose that we chose theta to be just some random number. I'll just go ahead and pick pi on 7. Now the left hand side of this equation is saying that if you feed pi on 7 into cosine and sine, and then square them, you should get 1. Now the input to this is pi on 7, so both of these are equal to pi on 7. Now I'll bring out my calculator and substitute pi on 7 into cosine. Now I'll just do the same thing for sine. Now that we know that the sine of pi on 7 is approximately 0.434, we can go ahead and square both the cosine of theta and the sine of theta. And now that we have both of the squares, we should just go ahead and add them to get the final value. So I hope you can see what this is telling us. Anytime we take a value, pass it through cosine and sine, square both the values and then add them, we will always get 1. Now that you understand what this is saying, there are actually 2 more Pythagorean identities that we can come up with really easily. To get the first one, we can go ahead and divide both sides of this by cosine squared theta. Now we can go ahead and break up the fraction on the left as well. Now we can just go ahead and cross off these cos squared thetas to make 1, and sine squared over cos squared is just the same thing as tan. And finally, 1 over cos squared is just the same thing as sec squared theta. Now remember, the way we got to this equation is by dividing both sides of this equation by the cos of theta squared. Now there is actually another really easy way to get to this formula over here. Remember, if you take this triangle and divide all of the sides by the cos of theta, you can actually scale it up to make this triangle over here. Now, if you remember correctly, the base of this triangle is exactly equal to 1, and the height of this triangle is equal to the tan of theta. This is because the sine of theta divided by the cosine of theta is just the same thing as the tan of theta. And finally, if you went ahead and divided 1 by the cosine of theta, this side over here ends up being the same thing as the sec of theta. Now if you just apply Pythagoras to this larger triangle, you'll find that 1 squared plus the tan of theta squared is the same thing as the sec of theta squared. And now we're ready for the final identity. If we go ahead and divide both sides of this equation by the sine squared of theta, we'll get another identity as well. Now again, we can separate the fractions on the left. Then we can go ahead and cross off the signs and realize that the cosine squared divided by the sine squared is the same thing as cot squared. And finally, we just realized that 1 on sine squared is the same thing as cosec squared theta. Now remember that we got to this final equation by dividing both sides of the original equation by the sine of theta squared. Now, in the lesson on the reciprocal trigonometric functions, I showed you another triangle that you can use to derive this equation easily as well. Now remember, to make this triangle, we actually rotated this blue triangle around its axis to fit over here. Now for this triangle, the height over here was equal to 1 because we just divided sine of theta by itself. Now just like this side over here was the tan of theta, this side over here turns out to be the cotan of theta. Now finally, just like this side over here was the sec of theta, this side over here turned out to be the cosec of theta. Now this diagram is looking a little bit cluttered, but we can still use it to get the main point across. By applying Pythagoras, we can see that the cotan of theta squared plus 1 is equal to the cosec of theta squared. Now that you know these Pythagorean identities, you can actually use them to simplify lots of expressions with trigonometric functions in them. I'm going to go ahead and give you 2 simple examples of this. Now let's start with this example. Suppose we're given sine theta plus cosine theta all squared. The first thing we can do is to expand out these brackets. So remember, to expand one of these, you just square the first term, square the last term, and then add 2 times their product to get the final result. Now we can go ahead and actually rearrange the order of these terms. And as we just showed, the sine of theta squared plus the cosine of theta squared is just equal to 1, so we can go ahead and replace this. And this immediately tells us that the sine of theta plus the cosine of theta all squared is exactly equal to 1 plus 2 times the sine of theta times cosine of theta. Now we can give you another example as well. This time we're starting with the tan of theta plus the cotan of theta. I'm going to start by writing them both in terms of sine and cos. Tan is just sine over cos, and cot is just cos over sine. Now to simplify this, I'll go ahead and use a trick. I'll multiply both of the terms by 1. Now sine theta over sine theta is just 1, and cos theta over cos theta is just 1. I use sine theta over sine theta because this denominator was sine theta, and I use cos theta over cos theta because this denominator was cos theta. And now if you look carefully, both of these terms have the exact same denominator now. Now that we've combined these brackets, we can immediately see that our numerator is the sine of theta squared plus the cosine of theta squared. So this is just equal to 1 again. Now we can actually go ahead and break this up into a multiplication of 2 factors as well. Now this term on the left is the same thing as the sec of theta, and this term on the right is the same thing as the cosec of theta, so we can make those replacements as well. And now that we've finished this, we can see that the tan of theta plus the cotan of theta is equal to the sec of theta times the cosec of theta. Now since these trigonometric ratios are related to each other in so many ways, it turns out that we can find lots of equivalences like this one that we found here. I don't even think it's possible to list out all of them, even if I tried. So it would be a good idea for you to learn to manipulate these expressions to find equivalent expressions like these ones. And with this, we've actually completed our discussion on the Pythagorean identities. They tell us that the square of cosine plus the square of sine is always equal to 1, and then from that we can derive these 2 other identities. And we can actually use all 3 of these identities to simplify any expressions that contain trigonometric functions. And with that, we've actually completed our discussion on the Pythagorean identities.